Previously, we looked at differential equations. And just to recap, a differential equation is an equation with a derivative in it. And once we've separated the variables in our differential equation, we can use various integrating techniques to solve a differential equation or find the function or equation whose derivative is given in our differential equation. Now, today, let's look at a slope field, which is simply a visual representation or a graph of a differential equation. And before we talk about the actual slope fields, let's make sure we remember what a differential equation looks like. So here's an example of a pretty basic differential equation. Now let's look at what's happening here. We're saying that dy dx, or the change in y with respect to x, is given by this equation 3xy. And what that means is that for any given point, for example, negative 2, 2, we can plug in our x and y values here. So let's just quickly do that. 3 times negative 2 times positive 2, and this gives us negative 12. Well, what does this represent? This represents the slope of the tangent line at the point negative 2, 2 of our solution or the equation. So the graph here, we can find the slope of the tangent line of the graph at the point negative 2, 2 using our differential equation. So what this means for us is that a differential equation can give us the slope of the tangent line at any given point of our particular function. So now that we have that in mind, let's actually look at how to graph a slope field. So remembering that our differential equation actually gives us the slopes of tangent lines, this means that these local tangent lines should do a really good job of actually approximating the shape of our function. And we talked about this concept previously with local linearity. So let's look at a couple of examples here. So let's look at this really basic differential equation. So I'm just going to highlight it here just to indicate this is what we're looking at. So let's look at the equation dy dx is equal to negative x over y. So at these points, can we find the slopes? So at the point 3, 2, for example, we know that our x is 3, our y is 2, and our differential equation says x over y, so 3 over 2, and then we are going to flip its sign. What about for part B? Our x would be negative 1 over negative 3, which is equivalent to just positive 1 over positive 3, and then we are going to flip its sign. So can you find the slopes for part C and D? Well, we should hopefully have found negative 2 is the slope of the tangent line at the point negative 2, negative 1, and 1 is the slope of the tangent line at the point negative 2, 2. Okay? So now what a slope field is a field of all of these tangent lines just graphed together or graphed on it. So for example, if we look specifically at this particular slope field, and you can see that it's partially filled in. I've already graphed a couple of the tangent line slopes here. So at A, for example, at the point 3, 2, part A, 3, 2, we can see a tangent line here that looks like it has a slope of about negative 3 over 2, okay? At the point negative 1, negative 3, negative 1, negative 3 now, I've got to graph the tangent line at the point negative 1, negative 3, and that slope is about negative, not about, it is negative 1 over 3. So that tangent line should look something like this. Now, if you have a hard time or difficult time graphing these tangent lines, what you could always do is you could just try to kind of sketch a larger tangent line. That is to say, we know that negative 1 over negative 3 should look something like this, right? That's the slope of a tangent line. So try to sketch something that's roughly parallel to that, right? And we see here that what we've sketched here does look like it's about parallel to what we've just sketched here. Okay, so that helps at all. So let me just go ahead and do that again. So negative 1 over negative 3 should look something like this. At negative 2, negative 1, we already see a slope of about negative 2. And at negative 2, positive 2, we should see a slope of a 1. So with that in mind, go ahead and pause the video and see if you can fill in the rest of our slope field. Now, if you've had a chance to do that, I'm going to go ahead and just put this on. You should get something that looks something like this. Okay? Now, as you're looking at this, again, this is the graph of our differential equation. It gives us all of the slopes of the tangent lines at any particular point. What we use a slope field for is to get a sense of what the solution to our differential equation is. That is, what is the function or a family of functions here that appear to be shown from this slope field. It looks like it's generating a function that looks like a circle, and it does look a lot like a circle. And let's actually see if we can show that analytically as well. So we said that our differential equation was negative x over y. If I separate our variables here, I should get y dy is equal to negative x dx. So previously we talked about how to solve these analytically. So we're going to go ahead and integrate both sides. And what we have here is y squared over 2 is equal to negative x squared over 2 plus c. Now, I can multiply both sides by 2, and actually let me call this c sub 1. We can multiply both sides by 2, and this would be y squared is equal to negative 2x squared plus c sub 2, where c sub 2, I'll just write that. Let c sub 2 be equal to 2 times c sub 1. And, oh, actually, there shouldn't be a negative 2 in front of this x squared. I apologize. So that should be negative x squared plus c sub 2. And if I actually move this all over to one side, I get x squared plus y squared is equal to c sub 2. And does this equation look familiar? Yeah, it's the standard form for a circle. So we see that this general solution to this general differential equation is indeed a circle, which appears to be what would be the graph of any function if we were to use the slope field. Now, can we find a particular solution? So that is to say, if I specify a specific point that I would like my curve to go through, so let's start with, for example, let me change this color, negative 1, 1. So the points negative 1, positive 1. So I want to sketch the graph of the curve that goes to the point negative 1, 1 here. Well, now let's sketch the solution here. So we know that our curve at the point negative 1, 1 will have a tangent line of about, or a slope of a tangent around, appears to be positive 1. So it's got to look something like this, okay? Now, as I get closer and closer to, as x decreases, as it goes towards negative infinity, notice what's happening to the slopes of our tangent lines. They are becoming more and more vertical. So we should see something that looks like this. And similarly, as we get closer to the x-axis, we see that they are also getting more vertical. Now that's kind of hard to approximate. Look at the slopes of the tangent lines. Kind of what I recommend to students is to think of a current and think of these tangent lines as little pieces of debris. So follow the current and try to sketch that tangent line. Whenever you're in between two pieces, try to sketch what you think is best approximation. So I'm going to go this way here. Now, notice here, I haven't sketched any tangent lines on the x-axis. Well, why is that the case? Well, if we're on the x-axis, that means y is equal to 0, and you can't divide by 0, so these tangent lines are undefined. So here, we want to sketch the largest possible domain. However, we cannot pass through an undefined slope. So we're going to stop here with an open dot. As we go around this way, notice what's happening with our tangent lines. They are flattening out. And in fact, on the y-axis, our tangent lines should be completely horizontal. Now, as I make my way around, I should see that it's, again, approximating, in this case, negative 1. And again, I have an undefined tangent line, so I'm going to stop here. Now, we want our solution, and let me kind of zoom in on this. We want our solution to have the largest possible domain containing that point negative 1, 1. And as a reminder, we cannot pass through an undefined slope. So we notice here that we have graphed this as a function. If I try to go all the way around and go this way here, I no longer have a function. I do have a graph, but it's no longer a function. So with that said, can we actually find a particular solution here now that I've graphed the solution using my slope field? And the answer is yes. If I go back and I take this equation, y squared is equal to negative x squared plus c sub 2, and I plug in the point negative 1, 1 for my x and y, I get 1 squared, which is 1, negative 1 squared, which is positive 1, but I make that negative, so that's c sub 2. So c sub 2 here is equal to 2. So I can then write my equation as y squared is equal to negative x squared plus 2. And actually, let's actually write that as a function. Let's go ahead and make this a little bit smaller so I have some space to work with, which would then mean y is equal to plus or minus square root of negative x squared plus 2. Now, since my function has to be going through the point -1, 1, this indicates to me that my function must be positive. So there is my particular solution. Here's my solution here. Negative x squared plus 2, and that appears to be really, and this, what we've sketched here on our slope field appears to be a pretty good graph of that function, y equals the square root of negative x squared plus 2. All right, go ahead and pause the video now and see if you can actually sketch the particular solution of the function that goes through 0, -3, and then find it analytically. So 0, -3, you should get a point that goes here. And let me just zoom in on the slope field so I have some space to work with. We start out pretty horizontal, but then we're going to start to flatten. We're going to start to steepen out, and it should be kind of going something like this. Try your best to graph it as best as you can. And we're starting to get more vertical here. We're getting more vertical. We're getting more vertical. And it should stop right around here where it's undefined. If I go the other way, same kind of deal. I'm going to kind of do something that looks something like this. Now, this is just a rough sketch, but you kind of get the idea. And you probably figured out, again, it should be a semicircle. Now, can we find that analytically? So let's do that. Oops. Okay, kind of accidentally zoomed out here. Let's do that. Let's find the particular solution here. So again, starting with y is equal to, or y squared is equal to negative x squared plus c sub 2, this equation. If we're plugging in negative or 0, -3, which was the coordinate, 0, -3, this y would become -3 squared. This x would be 0. And so c sub 2 would have to be equal to positive 9. So we said y is equal to plus or minus root negative x squared plus 9. And here we can see that, yeah, if our function goes to the point -0, -3, this should be the negative equation. And again, if you look at the general form of this, this would be x squared plus y squared is equal to 9. A circle with a radius of 3. And that appears to be pretty darn close to what we just sketched. All right, so hopefully this video kind of illuminates for you what a slope field is. That is a graph of a differential equation and how to sketch a slope field, as well as using a slope field to come up with the graph of our particular solution.